We now begin part 6.2, how a transformer works, or the functioning of a transformer. So you have first an alternating voltage applied on the primary side, right? And because the circuit is complete, alternating current will flow. Using the knowledge that you have learned from electromagnetism, when you have current flow, you create a magnetic flux. But because the current is alternating, you have an alternating magnetic flux in the primary coil. Because there exists a iron core donut, right, that links the primary and secondary side, this means that there is therefore an alternating magnetic flux on the secondary side. Next, you need to use your knowledge in electromagnetic induction EMI by Faraday's law, right? And an EMF Vs will therefore be induced in the secondary coil. So you see how the transformer is an amazing piece of device that uses a few pieces of knowledge, right? Both from EMAG and EMI. Next, because if there is a load connected across, the alternating voltage will then create an alternating induced current, right, in the secondary side. Okay. Next, if we assume that the transformer is ideal, right, we are assuming that there's no power loss within the transformer. We can say that the power input to the primary coil is equal to the power output on the primary coil. And therefore, we can say Vp Ip equals to Vs Is. And you can get this relationship. But you need to note that all these values can be both peak or root mean square values, which is to say if you're using the voltage on the secondary side over the voltage on the primary side, if you're using the peak value on the secondary side, you must be using the peak value on the primary side, and you should be using the peak current on the primary side and the peak current on the secondary side. In that way, you will not be making calculation mistakes, right? That means if you're choosing peak, you must choose peak values throughout. If you're choosing root mean square, you must choose RMS values throughout. Next, for ideal transformers, the relationship between the voltage P, primary side, and the output voltage on the secondary side, and the turns ratio, which is defined as NS over NP, right, is given by this equation. We will not be proving this, as the proof for this is way out of your syllabus. All right. So just so explain a little bit more, if your number of coils on the secondary side is more than the primary side, we call this a step up transformer, because the voltage output from this equation is obviously that the secondary voltage will be higher than the primary voltage. And the converse is such that if the secondary coils, the number of coils on the secondary side is less than the number of coils on the primary side, then the output voltage on the secondary side is lower than the input voltage on the primary side. We call this a step down transformer. Okay. So you have these two equations on page 15. We can actually combine them together to form this equation, right? That is very, very useful. All right. And I've included this equation in your summary page. Let's now look at example number 8. 10 lamps are rated 24 watts and 12 volts. So recall from lecture 1, 24 watts means that the average power is 24, and 12 volts is the root mean square voltage of the lamp, right? They are operated in parallel of the mains of 240. That means the root mean square voltage of the source is 240. Find the turns ratio of the transformer needed. So part A, right? If you want 240 volts on the primary side and 12 volts on the secondary side, and both are root mean square, we can use the turns ratio, NS over NP equals to VS over VP. Sub in the values and you get the answer straight away, that NS over NP is 1:20, right? I'm making a mistake here, right? Remember, in an exam, you should never give this in a ratio format. So it should be given as 0.05, right? So do take note, right? I read it like this for you to see the ratios more clearly. Next, part B, what will be the current drawn from the mains if the transformer is 100% efficient? So if the mains, if the voltage across here is 12 and the power of each lamp is 24, using P equals IV, right? P equals IV or VI, we can tell the root mean square current must be 2 amperes. Remember here, the average power is V. The average power divided by root mean square voltage is the root mean square current. Okay, so we get 2 amperes root mean square current. Since there are 10 lamps, the root mean square current on the primary side is, and the secondary side, right? Each lamp draws 2 amperes. So the total current on the secondary side, must be 2 times 10, 20 amps. Okay. Next, if it's 100% efficient, the power on the primary coil is the power output, right, at the secondary coil. And we know the secondary coil, right? We know that the root mean square voltage is 12 here. We have calculated the root mean square current, which is 20. So we can easily tell that the total power on the secondary side, or rather the average power, is 240. Since the root mean square voltage on the primary side is 240, this means that the root mean square current, the primary root mean square current, is 1.0 amperes. Okay. Look at the question. It says, what is the current drawn? And here, right, usually when you say current drawn, you're also referring to root mean square current. That's why we left it like this as the answer. Next, let's look at example number 9. Example number 9 is also the supplementary question number 1. Right, so after I explain this, you can try it again in supplementary question 1 and see if you can remember how to do this. Right, here in this question, the secondary coil of a 2-to-1 step down transformer is in series with 2 resistors, 40 and 80 ohms. This was a past year MCQ. Right, the alternating supply to the primary coil delivers a peak voltage, right? Very cheeky here, very nasty, 180 volts peak value. What is the average power dissipated in the 80 ohm resistor? Okay, MCQ, not so easy. Okay, so let's first take a look at how we can solve this. First, right, we remember, right, since we're going to calculate average power anyway, it makes sense to use the root mean square voltage. Okay, so first take the peak value on the primary side and convert it to a root mean square voltage. And we know that it's sinusoidal, therefore we can just take, right, what we have learned in part 4.3 and take the peak value 180 divided by square root 2 to find 127.3 volts. Next, we use what we have learned in transformers, right? The equation of turns ratio, right? Vs over Vp equals to Ns over Np. We know that Ns over Np is a step down, right? It's a step down transformer, so the number of turns in the secondary side must be half that of the number of turns on the primary side, right? Here we see 2:1, but when we apply it, we write it as 1:2 because the turns on the secondary side is less, it's half that of the primary side. So for every 2 turns on the primary side, there's only 1 turn on the secondary side. So once you have that, you can find the root mean square voltage on the primary side. You bring Vp, you bring out to the right hand side of the equation, so you have Vp times half. Okay, and you find that the root mean square voltage on the primary side is 127, as we've done earlier. You divide by 2, you find that the root mean square voltage on the secondary side is 63.7. Next, you want to find the root mean square current in the secondary coil. If you know the voltage, root mean square voltage on a secondary coil, the primary current, the root mean square current in the secondary coil must be the root mean square voltage in the secondary coil divided by the total resistance. So you have here the root mean square voltage that you have divided by the total resistance, you get this current of 0.531 ampere. Next, if you want to find the power dissipated in the 80 ohms, you just do a simple I square R, root mean square current squared times R. You get 0.531 squared times 80, you get 23 watts. Okay. And with that, we are done with part 6.2. Thank you.